Welcome to the last one, CS4510L14B. The topic is Kolmogorov complexity. Kolmogorov complexity is fascinating, and in the sense that you could really teach 3 courses on it. There's a book called Introduction to Kolmogorov Complexity. It's only an introduction to this topic, and it's like 900 pages long. It's like this thick. So in the preface of the book, they describe 3 syllabi in sequence of courses you could teach about such a topic. So there's a lot you could say about this topic, and we're just going to give you kind of a huge, like a big overtaste of like some of the minor topics in this field. Have you guys heard of the name Kolmogorov? Kolmogorov in any other context? He's famous for other things. Kolmogorov came up with the axioms of probability theory. He was the first one to really say events, sample space, all these random variables. This was all him. So he came up with those things. And in some sense, Kolmogorov complexity theory is really a probability theory free. It has no probability theory in it, theory of randomness. You can define randomness without defining probability theory, which is kind of like one of the morals of today, which is kind of strange. Also, he was gay. He lived in a 1-bedroom apartment with another mathematician, Alexandrov, on the river, and there was some famous story about getting blackmailed by Stalin or something. I hope they make a movie about it called The Luzin Affair. But the big guy wrote lots of, thousands of papers, a very lasting influence on what was the blooming field of what we call computer science today. He would have probably called cybernetics, which is just an old Soviet term for, they didn't have computers, so it was control theory, some differential equations in there. What we did with dynamic programming, they would do with Fourier series and things like this. So it was just computer-free computer science. It's kind of strange, but it is computer science, and it's prior to this. So what is the first problem we want to solve? It is a formalization of the notion of what it means for something to look random. So for example, I give you 2 strings. Okay, let's say I give you these 2 strings. Which one looks more random? It's not a formal question, but an intuitive question.
Intuitively, just set one.
Why?
Just because you see the presence of different ones and zeros, I guess.
Sure.
You can see patterns and
Yeah.
we just see all ones and oh, that's not random. It was chosen.
Yeah. If you were to describe the string to someone, it would take you longer to say the second string than the first one. The first one we may say has a short description. You can describe it to someone by just saying 10 ones. The second one maybe has a few different descriptions of it. Maybe it's maybe it appears in a binary expansion of pi at the 30th decimal place. Maybe it's, maybe you just say the string, There are many other descriptions of it, but they seem cumbersome, right? But from a probability theory perspective, what is the probability if you flip a coin 10 times that each of these strings appeared? Yeah, so in fact, this is, both of those strings appear with equal probability. So in some sense, we have an intuitive notion, and again, everything in this class has been about formalization of the intuitive notion, right? We have the real and the ideal in Plato. We have thought in the deductive sense, and then we go to logic. We have computing in the intuitive sense, and then we go to the Turing machine. Here we're talking about looks random. I don't know a better name for that in English. But the intuitive notion of looking random corresponds with what we'll talk about with Kolmogorov complexity. So Kolmogorov complexity just formalizes this notion of what it means for a string to look random, right? So intuitive, formal. We're just doing a formalization, right? In fact, what we seek is actually something kind of like a measure. And a measure, do you guys know the formal definition of a measure in the context of measure theory in mathematics and analysis? A measure is some function, let's say mu, from things, whatever those happen to be, to, let's say, either positive reals or perhaps naturals, such that it corresponds to some measuring of something, right? When we say, for example, if mu of x exceeds mu of y, then we would say x has more of it than y. And if we, for example, say that mu of x is equal to 0, then x has none of it. Right? Give me some examples of measures in any context. Functions that appear to satisfy this in the intuitive sense. Give me any function from any object that has properties like this.
Are you referring to like a unit of measurement or just like a property of measurement?
Give me any unit of measurement for any object. If you were to measure blank, what would blank be?
Just length.
Yeah, so classic one is length of intervals, perhaps, of line segments. Length is a measure. Give me another measure. Weight, let's say mass. Instead of length, we can also have area and volume. What else is a measure? Time, like into this context of time complexity?
Yeah, probably. Or just time in general. Like,
Yeah. There are more measures, there are more things that have this property. A lot of things that surprisingly look like this. I'll tell you another. The probability of an event is a measure. If a probability of an event is 0, it will never happen, so it has none of it, of no likeliness, right? Cardinality of a set is a measure. And that's kind of a strange measure because we have many cardinals, right? We have cardinality of finite sets is easy to do. Cardinality of infinite sets is going to be a little trickier, but it's of course possible. What else? We have entropy of a system. How chaotic is it? What else is there? I can't think of anything else, but that sounds. Can you think of any others go on that list?
Does time and space complexity counts for that?
Yeah, like you could define a measure upon algorithms about how many steps they take to define, yes. That's a little cumbersome though, because in fact the runtime is not a specific number itself, but a big O. So a function would go here and asymptotically would compare to other functions rather than something super nice, but that would definitely be possible. What else?
Memory.
Space used, yeah. That could also be a measure. I can't think of anything else, so let's just stop it there. We seek a measure on strings, and we want to measure how random they look, right? So we say that the Kolmogorov complexity is a mapping from strings to numbers, which defines some number such that if the number is bigger, the string ought to look more random. And if the number is smaller, the string ought to look simpler. For example, this string is simple. This string is complex. But there exist strings perhaps between those complexities. This one is simpler than this one, but more complex than that one, right? And so on. So it appears that there are measure-like properties. Now it turns out Kolmogorov complexity is not a formal measure, but it's like almost a measure. It's like off by a log or something. But we define what would be a good measure, like in the intuitive sense. When is a string hard to describe? Well, we may simply do, a string is random looking if it's harder to describe. So what we do is we take the Kolmogorov complexity to be the shortest description of that string. But what is a description if not just a program? So in fact, the Kolmogorov complexity of a string x is defined to be the shortest program P in any language, such that if you give that program to a universal simulator with the empty string, it prints x. This is a formal definition. Let's take another glance at it. We minimize over all programs. Which one is the shortest length? Such that the program, if given to a universal simulator, which will run the program on the string, on the empty string, takes no input. Does that program print x? So the question is, what is the shortest program that prints X? That is what we are asking, right? That is the complexity of a string, its shortest program. Why? Each program really is a description. So some strings are easy to describe, some strings are hard to describe. The description would correspond to a program, and that program is the description. So this is the function, that's it. I mean, this is a function you could write 900-page textbooks about. This is the function that you could teach 3 courses on, that's all it is. But it's so, we're just gonna do a surface level understanding of its depth today. But know that there is a lot you could say about it. We'll do some of that today. Question?
So K is your optimal compressor.
Yes.
Fancy.
We'll talk about exactly what, in an algorithmic sense, what does that mean later. But just know that's the definition of K. More questions on just the definition. Okay? This next thing you may ask is, there should be an obvious question you should have about this, which is, why am I talking about programs? Why am I not talking about Turing machines? And it turns out we have something we can call the invariance theorem. Which is that K is independent of any choice of language. So it's not a definition of what is the shortest Turing machine. And in fact, by the way, historically, this is an easy definition to come up with. You probably could have come up with this definition. And there are 3 people in history who came up with the definition at the same time. Kolmogorov came up with the definition. Solomonov came up with the definition, and he had a different use for it. And there was this guy named Chaitin who came up with the definition. He was like a high school student or something. And Chaitin and Solomonov did the theory in too specific of a way. Kolmogorov did it in the most general sense, and he did it the best, which is why we call it Kolmogorov complexity. Chaitin wrote a book where he repeatedly calls it Chaitin complexity. So he wants to name it after himself, but it's not he didn't do a good job, okay, to be honest. Shannon also has a theory that was something like state complexity, which is like the minimum number of specifically Turing machines, states, to produce a string, something like this. And it also was not as good. So we named it after Kolmogorov because he did it the best. That's what the K is for. But know that it's kind of like, there's this analogy that can be made that when an idea is so, like when the theory is ripe, the theory of computability had finished at this point, when this was being defined in the 60s. People well understood concepts of the halting problem and programming and things like this, even if they didn't have computers. They understood what was possible. So this kind of bloomed in several areas at the same time. Everyone kind of had the same idea because the mathematical environment at the time was ready for it. Right? The invariance theorem simply says that it does not matter what programming language you implement your complexity in because it is the minimum over all possible programming languages. Right? We can prove this. Suppose we had 2 specific languages. The 2 specific languages I can think of that are the most different are Python and Rust. Okay? So suppose we have 2 distinct complexities. A Python-specific one, which asks the shortest Python program to print X. We ask the K of Rust of X is the shortest Rust program to print X. Okay? So what it turns out is we seek a relationship between these 2 quantities, and that'll end up proving the theorem for us, right? Consider the following Rust program. Now, I don't really know Rust. There's an important property that Python and Rust both have. They are Turing complete, right? Why are they Turing complete? You could write a Turing machine simulator in Python. You could also write a Turing machine simulator in Rust. They're identical, okay? So, but by the Church-Turing thesis, you could technically write a Python interpreter in Rust. Do you agree? Now, suppose you take this Python interpreter, it's a giant inline function. Whatever it is, just put it there. But if there is a Python program to print X, there is also then a Rust program to print X by interpreting the Python program. Take no input. Okay? Let this Python program be not just any Python program to print a string x, the shortest Python program to print a string x. Pretty sure this works. Does anyone actually know Rust? That looks syntactically correct, right? Okay, fine. If this is the shortest Python program to print Rust, we have not the shortest Rust program to print x, but we have a Rust program that prints x. So in fact, we can upper bound the complexity of Rust, right? We don't know what this is equal to because we haven't given a Rust program for x. But we know that this can be upper bounded by this program. This is a program to print x. We agree? Because this is a Python program to print x. So this is a Rust program that prints x. So we can upper bound the complexity by the size of this program. So what is the size of this program? Well, it's going to be the length of this string, which is what? Yes. Okay? Plus this interpreter. Plus some constants for this f of n main. This is an enter, new line, some other little delicate pieces there, okay? What is the size of this program, Py in Rust? What is the size of the Python interpreter as a function of x? This is a trick question. How big is the C compiler as a function of the input that you give it?
Constant.
Yeah. This does not change no matter how long the string x does. This may change. This inline function will never change. So, in fact, we know that the complexity of Rust of x is less than or equal to the complexity of pi of x plus some constant. Okay? So we can get a Rust program by getting the shortest Python program. We don't know if there's a shorter Rust program or not, though. But we know that it's upper bounded by this. Similarly, although you can write a Python interpreter in Rust, you can also, I don't know why you would want to, but you could write a Rust compiler in Python. Do you agree? Why universality? It technically is feasible. It should never be done, but it could be done, okay? That's sufficient to prove that the shortest Python program must be less than that Rust program plus the size of the compiler, Python compiler, the Rust compiler written in Python, which is also a constant. So, if we know that this is less than this by some constant, and this is less than this by some other constant, we know that k of, I'll put it here. Well, we know that the complexity of Rust of x minus the complexity of Python of x is less than what? How different are these? How much could these differ by? It's going to be at most a constant. So in fact, this is the invariance theorem. The complexity, the shortest description of a string is not a function of any language that you would choose. It is only a function of the string itself, is what we've proven. So in fact, similarly, while every useful language that can simulate a Turing machine is Turing complete, and the only difference of choice of languages are in fact accessibility features, like, okay, Rust has memory safety, Python is easier to write, this library already exists in this language. Those decisions determine what language you choose, but they're all technically feasible by Turing completeness. Here, it says something stronger. In fact, the shortest program in each language cannot differ by at most a constant. So, to extend this, binary search in Rust is approximately the same size, code-wise, as binary search in Python, which is perhaps something you would expect because those are both like structured serial languages. But this is true for any weird exotic language you choose. The program's code is going to be almost identical. This is the invariance theorem. The choice of language does not matter. Therefore, we may drop this language-specific subset and define the actual complexity k of x to be the min over all possible languages that would be chosen. Questions on that? invariance. Okay, let's actually compute some lengths of strings. For any string x, what is the complexity? Give me an upper bound on the complexity of x. Give me any program that prints any string x.
Any program at all
Yeah.
prints X.
Yeah.
Just print X in Python, I'm assuming.
Is that a program that prints every string x? So what is the length of this program? It's approximately the length of x plus c. If x is longer, so is this program. If x is shorter, so is this program. It doesn't mean you can't do better, but at least there is a way to print every program. Just print x, okay? What about if you concatenate x with itself? What is the length of the shortest program that prints xx? Well, here's one thing you could do. Okay. Hard code XX and then just print it. But that's not the best program. Give me a shorter program that prints this. Prints XX.
Use the first definition of the function and then just call the function twice.
I'll say the same thing. Store only x and then compute xx from x by calling it twice, essentially. So given x, if you want to print xx, you don't need to have a program of length xx. You can have a program of simply length x and you can compute xx from x. This is sufficient to prove that the size of this program is length of x plus, say, some c prime. Now we say c prime instead of c here. You shouldn't do this ever, but I'm going to mention it one time only. This program has slightly longer length than this program. So these two constants are different. But the constant is something that is language specific and independent of x itself. It's not like log of length of x or whatever, right? The difference between these two is really this symbol here where you have to print x. The extra additional constant needed to compute xx from x, right? What else? What about a program that prints n copies of x, okay, of x to the n? Describe to me a program that does that.
We just make a for loop of n times, and inside it just print X.
I thought you could also just multiply, I think.
Okay. That's going to be ugly, but let's just say it works.
It's like,
I'm pretty sure that works in Python.
it works in Python. It's like,
I hate
Yeah,
Python.
That's not quite, that's going to insert new lines. Forget it. We know what we're talking about. Okay. What's the size of this program? Again, we don't care about time. We don't care about anything except size.
x plus n plus some constant.
The length of x plus, we could say the length of n. But what is the length of n if n is a number? How many bits does it take to encode a number? Log. So when it's a string, we'll say the length of x. When it's a number, we'll say log of that number. Okay? Those are the same thing, really, but just convention. Okay. Can you improve this? Yeah. What if x and n have short descriptions? So what you can do is replace these two lines here with let x take on something returned to by f, and then take on something returned to by g, where f and g are the shortest programs that return x and n respectively. You can then improve this to be whatever smaller description is there. So for example, if x was highly compressible, had a shorter description than itself, you could put that here. Right? So this is technically a better bound than this one. Right? Now what if I asked you for the reversal? What is, let's say, x reversal? Give me an upper bound on the complexity of the reversal of x, perhaps as a function of x.
The length of x?
You could improve that, in fact, to what?
Half the length of x? Or
Well, you don't actually know anything about x. It's as most general as possible. But the answer I'm looking for here is that this should be just k of x. If there's a shorter program that prints x, this is a program that takes x, does whatever that's going to do, and then adds an extra thing that reverses it, which is a constant. So these are related by a constant, right? So some strings appear to have short descriptions. Some appear to have not so short descriptions. So, but this is how you can always kind of like, to upper bound the Kolmogorov complexity of a string, all you need to do is to describe a program and kind of estimate its length as a function of x. Similarly to given a problem, how do you estimate, the big O is an upper bound and you just give a algorithm for it, it's gonna be some upper bound, right? Same thing is gonna happen here. Now the question is which strings have short descriptions and which strings do not? So this is a difficult question because the whole point is which strings are in some sense simple and which ones are complex. That's the whole point of the question that we're asking. So rather than just immediately tell you this, let's kind of estimate an upper bound. So let's fix strings of length n. Suppose I ask you for as a ratio which strings are compressible, right? So consider the set of, how many strings of length n are there? Well, let's ask just for sigma to the n. And we seek how many of those strings of length n are compressible by, let's say, 2 bits. There's a shorter description of W that can be compressed by 2 bits, right? So we could describe this as W is in sigma n, such that the Kolmogorov complexity of W is less than or equal to the length of W minus 2, right? So which string, certainly there is a program of size W for each W, right? That is the basic program that simply prints the string, plus a constant, forget it. But what programs have what strings have programs that print them that are shorter than just saying it out loud, by at least 2 bits, right? But if we know that the complexity of the string W is less than the length of W minus 2, the definition of the complexity of W is in fact the shortest program that prints W, right? So in fact, we can upper bound this if there's a program that prints W that has a certain length, then there is a program that prints W that has a certain length. So we can upper bound this set of strings by programs that print those strings, right? Consider then P is a program such that the length of P is equal to what, n minus 2? Do we see what we're doing here? We upper bound it actually significantly. We seek a program of a certain length and a certain behavior. We can upper bound that simply by programs of a certain length. Okay? Now, what is a program if not a string, right? So every program, we can now significantly upper bound this by considering it instead of programs, syntactically valid, passing the syntax check or whatever, just consider all strings of up to that length. Okay. Do you agree so far that we've correctly overestimated the number of strings that are compressible by 2 bits of length n as a ratio? Okay. What is sigma to the n, cardinality-wise? Sigma let be 0, 0, 1. What is sigma to the n? How many binary strings are there of length n? Union, you may be able to know this immediately, but we can replace, these are all disjoint. So we can replace the cardinality of this union by a sum of cardinalities. Right? And what is that then? Does anyone remember?
Approximately 2 to the n-2.
I'll write it down extra step. We have 1 string of length 0, 2 strings of length 1, 3 strings of length 2, no, excuse me, oops, no, 4 strings of length 2, 8 strings of length 3, and that is going to be, the last strings is going to be of length 2 to the n minus 2, right? So this sum is going to be, and it's an overestimate, so it doesn't really matter how precise we are, but this is going to be, what is this sum going to be?
2 to the n-1 minus 1.
Is there a minus 1 here?
No, I think just 2 to the n minus 2 minus 1. Yeah, that's just it.
I think that's it. I think that's it. No, there should be a minus 1.
Should be a minus 1 because there's the 1 in this.
Okay.
Yeah,
Now
I
watch
think that's
this.
Yeah.
Okay? Ignore it because we're overestimating. What is that? Oh. That is really bad. So I asked for a ratio of strings of length n that are compressible by 2 bits. Half of them are. And this is an overestimate. So only half of the strings are compressible by 2 bits. That means the other half are not compressible by 2 bits. So half the strings basically cannot be compressed. For each, and this is independent of n. This is for each n. Suppose I asked you to repeat the analysis for compressible, not by 2 bits, but by, let's say, d bits. What fraction of strings are going to be compressible by d bits? What would change here? This would change something, sum to n minus 2 would be n minus d, right? And then you would get n over d, n to the 2 to the n minus d over 2 to the n. You would get something like 1 over 2 to the d minus 1, something like this, right? For d not 1, d is 2 or more. This is very small. So if I ask you how many files of a gigabyte can be compressed by a byte, I'm only asking for 8 bits. I'm asking for nothing. How many gigabyte-sized files can be compressed by a byte? Basically none of them. Like what is that, 1 in 2 to the 7? That's like 1 in 300 or something, right? But that's independent of n. So if I asked you which files of size 10 terabytes can be compressed by a byte, the answer is the same. So what we can see here by this counting argument is most strings are incompressible. And this leads to Kolmogorov's probability theory-free definition of randomness. A string is algorithmically random if for some constant c the complexity of x is not too much less than that. Okay? Essentially, a string is random if its shortest program is just saying the string out loud. Okay? think about it, how this corresponds in a probabilistic sense. When does the complexity significantly dip below this? Which strings have very short descriptions? That string has a very short description, but it is also incredibly unlikely. So the compressible strings are a fraction of all strings. There are very few compressible strings, and that corresponds that it is incredibly unlikely that you will ever hit that exact string were you to flip a coin, right? What is the probability if you flip a coin an even number of times, do you get a sequence of the form XX? We know XX is compressible. It has a shorter description than its length by exactly a half, in fact. But what's the probability you flip a coin an even number of times and you get a sequence that looks exactly like itself repeated twice? That is itself a statistically unlikely event. Similarly, what happens if you get a number that's the binary representation of a prime number? Or let's say the first 30 digits of pi or e or something like this, right? So there's all kinds of strings that have short descriptions, but they are, in a probabilistic sense, incredibly unlikely, right? So the strings that are algorithmically random are basically almost all of them, except those that are not. If you have a short description, you're not algorithmically random. If you have no short description, which is most of them, then you are algorithmically random. Think about what a random string looks like in terms of JPEGs. If you were to uniformly sample a JPEG, pixel by pixel, it would look like TV static, right? So images that contain information are exactly those which do not appear algorithmically random. For example, a picture of a parrot would have a very large splotch of red. A picture with information would be one that is highly compressible and highly non-random. Information that is valuable is one that is not random in some sense. It's kind of the opposite perspective of information theory. But a compressible string is an incompressible string is a random one. That is the definition of randomness, and we see that's kind of like how it corresponds to that, right? In an intuitive sense. Why do zip file algorithms work in practice then? If you take a file, why is it the case that the zip file is smaller? Because the information that, if you take all files of a fixed length n and you compress them, but with the zip file algorithm, which is not perfect, but it approximates a smaller description of that object, the zipped file is its smaller description, right? So why does that work is because even though most strings cannot be compressed, most of the strings humans interact with on a day-to-day basis can be compressed. And it's very unlikely you'll encounter a purely random string in your day-to-day computing. When you have a text file, it has repetitions of letters and words. All these kind of algorithm techniques work in practice when they can never work in theory, right? Questions about that?
Does that mean it's like theoretically possible to create a file that you can't compress with zip?
Yeah, absolutely. In fact, such files must exist. Let me give you, I can answer your question in a stronger sense, but we'll do so in a second. Let me give you 4 properties of Kolmogorov complexity. We can actually plot this function f. Suppose instead of, just so the axi are not messed up, and suppose instead of strings to numbers, we just went numbers to numbers. And we asked for the shortest program to print that number. It doesn't really matter, it's a binary string, it's the same thing, right? But we notice then that we can talk about it like an actual function when it does this. So there's 4 important properties that it has. 1, k hugs log of n. Most strings are incompressible. So most of the time, the shortest description of a string is what? Just print the string, right? So for most of the time, it does this. That program that we described earlier, just print n, hardcode n printed, is the best program for most strings. So most of the time it does that. 2, k dips infinitely often. So there are arbitrarily large, long strings that have arbitrarily low complexity. Why is this the case? Consider k of n is approximately k of 2n. Why? If you have a program that prints n, you have another program that differs from that one by a constant that prints 2n. By taking that program, running it, and then multiplying its output by 2 and then returning that. which is approximately k of 3n, which is approximately k of 2 to the n, which is approximately k of n plus log n, square root n, whatever, right? For each n, these are all approximately the same, right? So although it hugs log x, it also appears to dip infinitely often. 3. K of x grows in the sense that it's even though it may dip, its trajectory is still upward. Why? Longer strings should have longer complexity. Do you agree? Okay. 4, it's kind of continuous. What we mean by this is it's a discrete function. It can never be continuous in a formal sense. But what's the definition of continuity? It's like if x minus x naught is less than delta, then like f of x, I'm not sure if I remember this exactly, but is less than some epsilon, right? So like if x and x naught are close, like if you have a function that's continuous, right? If this is x and x naught, this is going to be f of x and f of x naught, right? So if x and x naught are close, then f of x and f of x naught are close, right? If you've ever tried to plot a hash function, it looks like this. Right? I would encourage you to take a look at what a really random function looks like. But Kolmogorov complexity is kind of continuous because k of x is related to k of x plus or minus 1, right? Because the shortest program that prints x is up to a constant related to a shortest program that prints x plus 1 and x minus 1. So the complexity of the next string cannot be too different from your own because there is at least a program that prints that one that differs from that by a constant, right? Given these 4 features, we kind of can estimate a plot of k of x as follows. First, it hugs log of x. So let's plot the logarithmic function. And we know it maybe looks like this. Something like that. So that's what the kind of the plot of it looks like. Maybe it dips too often. Maybe I should make it dip less often. Something. But most of the time it's touching this, right? Now, why am I talking about it this way? Like we can plot it. Why have I only been able to give upper bounds of the function? If you had to guess why, what would be the reason?
Your question is why can we only provide an upper bound?
Sure, or why have I only provided an upper bound?
I guess it's unsolved. There's
Yeah.
like no lower bound or no useful lower bound that you can provide other than 0.
Not only is it unsolved, but it is unsolvable. Kolmogorov complexity is an uncomputable function. There is no algorithm that computes the shortest program. Proof assumed to the contrary that the Kolmogorov complexity function is computable. And recall the definition of a function being computable is that there exists a Turing machine which takes as input something and halts with the output always, right? So here we can construct the following program. M on input, let's say nothing. What we're going to do is obtain the code of M via Kleen's recursion theorem. And we want to ensure that we print a string which has complexity longer than we're supposed to. So for x in sigma star lexigraphically, if the complexity of x exceeds the length of m, print x. Okay? So what happens here? M searches over all strings that have complexity longer than itself, and it prints the first one. So we know by this property, actually I'll get rid of that equals 2. Just print the first string that has this property, right? Maybe the 10th string, doesn't really matter. But x has the property that k of x exceeds the length of m. Why? I mean, that's why we printed it. But what else do we know must be true?
The complexity of m is greater than the complexity of x?
Perhaps. But what do we know? What is the basic behavior of M? What does M do? M prints X.
It prints the
We actually can say something about the complexity of X because M prints it. M is a program that prints X.
So it must be, yeah, the complexity must be.
It's a program that prints the complexity, right? Okay. Contradiction. Print the first string, which is longer complexity than me, but I'm also printing it. Not good. You can actually avoid the use of Kling's recursion theorem here with a more detailed construction. What you do is instead, you let this constant be C, and then you let the C go here, okay? You leave the program incompleted. Now, were you to put a number there, you measure the length of M, and then you try to insert the length of M, okay? The problem is, though, that as you insert the length of M, that'll change the length of M. So that won't be exactly right. So it's a little careful, you could do a very careful programming thing where you have some C overestimate the length of M significantly. And you can do so by inserting it and not actually changing the property. It's a little detailed programming thing, but you can avoid the use of the recursion theorem by such a property being true. What's the name of this technique? I guess it would be diagonalization, although that is not quite obvious because we've contained the diagonalization in the application of Kling's recursion theorem. That did all the diagonalization for us. We didn't have to think about it any more than that, and we can just call it for free. But in some senses, it is true by a diagonal argument. Right? Questions on that so far? Okay. So why do we care about Kolmogorov complexity? Again, you could teach 3 courses on this function. I won't ever do that, but it's just fascinating to me the properties it has. One of the important properties, and this is again just my opinion, I get to do whatever I want. One of the properties I think that's fascinating is that it enumerates a very interesting proof technique. Are any of you familiar with the probabilistic method? Probably not at this level, but the probabilistic method is a technique where you can use probability theory to assert the existence of an object. You say an object exists with non-zero probability, therefore it exists. So you use probabilistic argument to argue about existence of, for example, graphs with cycles and things like this. Kolmogorov complexity, in some sense, can be used, what's called the method of incompressibility. Can be used to argue as a proof technique for many, many things. In the sense that since a random object, on average, has very high Kolmogorov complexity, you can use that to statistically say something about a group of, a set of objects in an average case, rather than a specific case. I'll give you 2 interesting proofs of this. One is there are infinitely many primes. Okay? Does anyone remember, this is a trivia question, who first proved this? At least written down. Euclid. It was Euclid.
Yeah.
And do you recall the proof in 300 BC? The proof goes, assume there's finitely many primes and consider this number P1 to Pk plus 1. That somehow is not prime because that you can show it's not prime because it's not equal to any of the finitely many primes. It's bigger than all of them. It is also not divisible by any of the numbers. So it also cannot be composite. It's going to reach a contradiction. I won't enumerate this now, it's in my 2050 notes. But this is kind of what he does by contradiction. We can do a similar thing using Kolmogorov complexity. Suppose there are only finitely many primes. P1 to Pk. We still have the fact that for any n, there exists E1 to Ek such that n is equal to P1 to the E1, Pk to the Ek. Agree? If there are finitely many primes, it is still the case that each number can be written as a product of those primes, right? So in fact, this set E1 to EK describes n. Right? Here's the program that prints n. Right? Brute force for P1 to PK. Return P1 to the E1 times times PK to the EK. Would you agree this is a program that prints n? It has hard-coded these prime powers. It then brute force searches for the primes, which exist, and since PK is constant, that doesn't really matter, and then it returns the product of these primes and their powers, okay? Let's estimate any EI. So what is an estimate of EI in terms of n, right? What is the biggest value that an EI could take? EI could be at most, it could be the case that if n is this product of prime powers in such a way, the simplest case would be that there's a single prime power, right? So we would say like Pi to the EI is equal to n in the simplest case, right? The largest EI could be, and in fact it would be Pi's too, but let's just consider there's a single prime power. It would be then that EI is approximately log of Pi of n, right? Which is approximately of O of log of n. So EI is approximately log of n. Agree? How many bits does it take to encode EI then? So what is the size of EI? What is the complexity of EI? If E of I is less than log of n, how many bits does it take to encode E of I?
Log of n?
Log of n. So, the size of this program is simply going to be the encodings, right? The complexity for any n is going to be the complexity of E1 plus the complexity of EK plus O of 1, right? Each of these is log n plus log plus O of 1. If you have k logs and you sum them up, that's just k log n, which is still O of log n when k is a constant. So in fact, we get that k of n is O of log of n. What's our contradiction?
Because it returns and it cannot be like that small.
Yeah, this is too small. Most numbers, in fact, are incompressible, right? And this is important. Most numbers cannot be compressed. So we know for most numbers it is true that they cannot go 2 below log. Maybe like a bit or 2, but that's it. Most numbers are incompressible, yet we claim all numbers can be compressed. Contradiction. Could we compress a number too small? If there was finitely many primes, we could perform such an encoding and describe each number in much fewer bits than we could just by having the bits by themselves. The prime powers would encode the number smaller than you could do so in binary. Because you would encode a tuple of numbers that are much themselves smaller. Problem. It doesn't work. We know it doesn't work because we gave a counting argument that most strings are incompressible. So this must be the case, but these two exist in contradiction. Done. Questions on that? Just kind of a cute warm-up thing. Very surprising fact. In fact, the infinitude of the primes, there's a paper that had like 80,000, not 80,000 proof, but it had like 40 different ways to prove that there's infinitely many primes. This was one of them. There was another talk, by the way, of a physicist who was trying to prove that certain theorems can be proven true, quote unquote, using laws of physics. And such an argument could be made not based on the Kolmogorov complexity of strings, but the entropy of something. Because we know that the entropy cannot be below a certain amount, something like this. But if there were finitely many primes, you could perform such a trick and do some arguments about entropy. Okay. I'll do one more example of the application of the method of incompressibility, which is going to be basically what we did. Assume to the contrary something, use that as an algorithm to make an encoding of something way too small, derive a contradiction. What are we going to do? You've seen this one before. A to the n, b to the n is a natural, is not regular. We did that like way in the beginning. We can prove it to be not regular by the method of incompressibility. Assume to the contrary, it is regular with DFA D. Run the DFA on just A to the n, okay? You stop at some rejecting state, say Qi, okay? Now we can use the DFA and the state Qi as an encoding of this number n. Why? Suppose you're at Qi in the DFA and you repeatedly take B transitions. What will happen? Okay? If you repeatedly take B transitions from Qi, you got to Qi by doing A to the n, right? So this first transition will put you at A to the n B, A to the n B B. All those should be rejected, right? But there will be a single time where it is exactly A to the n B to the n, which will be accepted. A to the n B to the n minus 1 should be rejected, and A to the n B to the n plus 1 should be rejected, right? So you can use this to determine n just from this intermediary state. If I were to describe the program, it may be like this. Def F has hard-coded this state D, the DFA D, and let's say this Qi is something like that. We could say Q takes on Qi, and we say counter is equal to 0, while true, we would say if Q is accepting, print C, else we repeatedly update this. Do you agree that this prints n? This Q takes on delta of QB, basically updates the current state. This is like the cursor state. We're at this state Q. We apply the transition function from that state with a B transition, apply that with a B transition, apply that with a B transition, apply that with a B transition. Eventually, if we hit an accept state, we just print the counter, right? So what we determined Qi by first running the DFA on A to the n. So this machine F prints some n such that A to the n, B to the n accepts in the DFA, right? Because it counts exactly the right number of B's. It can't be less than or greater than this, but it counts that exact number of B's. What B to the n from Qi will get you to an accept state? It's exactly n B's, right? What is the size of this program? This prints n for any n. It's less than or equal to the size of the DFA plus the size of the current state. That's that state where you run A to the n in, plus some constant work. What's the size of a DFA as a function of n?
It's just a constant.
Yeah. What's the size of the state as a function of n?
Also.
Yeah. Every number is constant size, contradiction. That can never, of course that's ridiculous. So if it were regular, in fact, what are we talking about here? The configuration of a DFA is simply a single state. So if you know a partial configuration, you know the next time you'll reach an accept state must be exactly after n transitions. So what you can do is just count those n transitions and you know n. But that's a contradiction because this could be a way to encode every number, infinitely many numbers and only finitely many bits, which of course ought to be impossible. The DFA plus the state somehow uniquely give you an encoding of every possible natural number. Impossible. Contradiction. Right? Any questions on Kolmogorov complexity? All right.